All right, as I was saying, the identity matrix is one of those cases where you can multiply a matrix times the identity, or the identity times a matrix. You can flip the order there, and you get the same thing, just like multiplying by 1. So you just swap them back and forth. The zero matrix is another special case. A matrix times 0, or 0 times a matrix, gives you the same thing, 0 in both cases. The determinant of a matrix is very important. So for a 2 by 2 matrix, if we look at the elements A, B, C, D, the determinant of that matrix, which is, again, we mentioned the straight up and down lines. The straight up and down lines means that you're going to do the determinant. It's not a matrix, it's taking the determinant of that matrix. And it's just defined for a 2 by 2 as A times D minus B times C. You notice that that's going to give you a scalar. This is just a number and a number, a number and a number. It's going to give you a scalar value. So for 1, 2, 3, 4, the determinant of 1, 2, 3, 4 is 1 times 4 minus 2 times 3 gives us 4 minus 6 is negative 2. A 3 by 3 determinant is a little more complicated. A, B, C, D, E, F, G, H, I. What you're going to do is have 3 2 by 2 matrix determinants. So the determinant of this crazy big 3 by 3 is just the first element A times the determinant of E, F, H, I, which is the matrix when you remove the row 1 and the column 1. So you remove this row that A is in and this column that A is in, and you're left with E, F, H, I. Do that determinant right there, which is just E times I minus F times H. Then you have to subtract. This is key. People forget to subtract the second element. The second element is subtracted, and it's going to be a negative B. You remove that B row and that B column, you end up with a matrix that's just D, F, G, I. D, F, G, I. So you do that little determinant. Then you add to that C times this 2 by 2 determinant. C, you have to remove this row and this column. You're left with D, E, G, H. You get a 2 by 2 determinant there. For this example, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we go through the whole thing, 1 times the determinant of 5, 6, 8, 9. 1 times 5, 6, 8, 9. Minus the 2 times the determinant of 4, 6, 7, 9 after we remove that first row and second column. 4 times 9 minus 6 times 7. Plus 3 times the 4, 5, 7, 8. We remove the first row and the third column to get a 2 by 2 matrix. So when you do these 3 2 by 2 determinants, you get 5 times 9 minus 6 times 8. And you get 4 times 9 minus 6 times 7. And you get 4 times 8 minus 5 times 7. And once you do all that, those number crunching, you get 0. 0 is an interesting value for a determinant. Just like a dot product, a 0 meant something. Determinant dot product means something. Now, let's talk about unit vectors. In 3D problems, in 3D space, your unit vector defines your x, y, z directions. And a lot of times we call these bold I, J, K. So the x direction is 1. The j has a, for the x direction, it's just I equals 1 in the x element. For the y direction, there's a 1 in the second element. And the k direction, it's a 1 in the third element. So x usually goes to the right, y goes up, and z comes out of the board in most basis when we talk about x, y, z. Now moving on to a cross product, it's sort of like a dot product. If we have two vectors, we need to figure out a cross product in some cases. So the vector cross product is a different type of multiplication. We have vector A and vector B. Ends up being, it gives us a new vector. A dot product gave us a scalar. A cross product gives us a new vector. And that new vector, if we think of the plane between A and B, so A and B, if they aren't on top of each other, they define a plane in 3D space. So that plane is a big flat plane, but the A cross B defines a vector that sticks out of the plane. So A and B, no matter what direction they're going, as long as they're not on top of each other going opposite directions, exactly the same, they're going to define a plane. And the A cross B calculation for the cross product gives you a vector that goes out of the plane. How do we actually do this? Well, we have to know determinants to do this. So we write down A cross B is going to be I, J, K. And we set that up with the elements of A, the x element of A, the y element of A, the z element of A, the x element of b, the y element of b, the z element of b. And then we do the same thing with the determinant. I times the determinant of these guys, ay bz minus az by. J, which is the y unit vector, times the determinant of ax times bz minus az times by. And then we add k, the z direction unit vector, ax, by, ay, bx. So we get three basically components: a component in the x direction, a component in the y direction, and a component in the z direction. Let's do a little example. So if we have 1, 2, 3, 0, 4, 2, two vectors we want to do a cross product. If we have that cross product, then when we do the cross product, we set up as the determinant of a matrix, 3 by 3. We have I, j, and k, which are actually unit vectors. 1, 2, 3, which is vector A. 0, 4, 2, which is vector B. I times the determinant of 2, 2, 2, 3, 4, 2, which is going to be 2 times 2 minus 3 times 4. Subtract j. Remember, it's the second element's always subtract. So you have a subtract j times, remove this row and this column. You get 1 times 2 minus 3 times 0. That determinant of 1, 3, 0, 2. Plus k times the determinant of this matrix, 1, 2, 0, 4. 1 times 4 minus 2 times 0. When we calculate out those three different determinants, you're going to get 2 times 2 is 4, minus 3 times 4 is 12, which is going to be negative 8. 1 times 2 is 2, minus 3 times 0 is 0, so it's going to be 2 times 0, but it was a negative value for that second component, so it's going to be negative 2. And the third one is 1 times 4, minus 2 times 0, which is going to be 4. So this is the description of a vector that points out of the plane from this A and B vector. The plane determined by A and B, this describes a vector that points out of that plane following the right-hand rule. If you point A with your fingers and you go to B, the resulting cross product is going to be your thumb using your right-hand rule. So A points this direction, B points this direction. The result of A cross B is going to be this thumb. Right here, just like I said. So I cross J is equal to K. So if we have I cross J, in this case, X is out of the board and Y is to the right. So whatever result you're having, we should get the value that goes out of the plane. So in this case, if we have 3 times 1 times 2 times 4, that's going to be the dot product of those two. 3 times 4, dot product. We have to do the elements. 3 times 2, which is 6, plus 1 times 4, which gives us 10. So it's a value greater than 0. And the best answer here, a 2 by 2 matrix, if we do the determinant, we do 1 times 5 minus negative 1 times negative 2. 1 times 5 is 5, minus a positive 2. See, 3 negative signs there is going to be a subtracting. 5 minus 2 is 3. Why do we do this? One of the things we've used a lot of work on is looking at biological application. We have looked at cell staining, and each one of these images is just a matrix of values for intensity. So cell staining inside the nucleus. So you stain the nucleus, and you end up with an intensity value, and you have to go through that matrix and look at values inside there. We also use it for modeling a lot of different things. There's some nice applications where you can take these values, and we looked at modeling the intensity outside the nucleus as a function of distance, and that involved some of the matrix math. Here's another example of modeling where we looked at a biological reactor. Example for glucose response to insulin injections or bioprocess production. So we change the flow rate and we're looking at making a pharmaceutical. We can come up with a linear model for the output of the response that depends on the inputs U. Given a lot of data, we can set up a big linear algebra problem where we have a matrix and a vector and a constant vector and solve a set of linear equations by using something called the matrix inverse. So this linear algebra stuff can be very, very useful. Another one is another example from a paper we wrote where we had a particle interaction. When you're granulating a pharmaceutical, you have this type of coalescence where you have different parts of particles go together to make bigger particles, and sometimes they break. So we can set up the uncertainty or the problem with lots of measurements in this form. Using ax equals b, we can solve for x and solve a set of linear equations with lots of unknowns and lots of equations all at once. Thank you very much.